that we have x minus y. We can represent this as if we say x minus y is equal to x plus negative y. That's going to be the same thing. So then we can use the addition algorithm, but we need to have a way to represent this negative number as a binary. So there's three main ways that negative numbers are represented as binary numbers. And so I'm going to give you the three ways, and then we're going to go through each of these. And basically, so there's the signed magnitude representation, 1's complement, and 2's complement. And I just want to go into what these are, because I think once you see what they are, it'll make sense. So with the signed magnitude representation, all we do is represent if the number is positive or negative with a bit. So we use the most significant bit, and so remember the most significant bit is the bit on the left of your byte, and we say that it's 0 if the number is positive and 1 if the number is negative. So let's go look at these numbers. So for the positive numbers, we have 0 through 7, and we have simply set this first bit, the most significant bit, equal to 0 to indicate that those are positive numbers. And then for the negative numbers, we've taken this most significant bit and set it equal to 1 to represent that these numbers, this negative 0 through negative 7, are negative numbers. So just right off the bat, can you see some problems with this? We're wasting one of the bit patterns because we have 0 represented twice. 0 and negative 0 are the same thing. So we're basically using an extra bit pattern that, like, we're wasting a number that we could potentially use for something else. So the negative is that we're wasting one of the bit patterns. The other issue with this is we can't just perform subtraction by addition alone with these numbers. And I'll show you why. So let's say that we want to, let's say we have 7 and we want to subtract 2. So let's say we want to do 7 minus 2. So 7 is 0, 1, 1, 1, and negative 2 is 1, 0, 1, 0. So this is equal to 7. This is equal to negative 2. So let's add those together. So we have a 1 and a 0, so we get a 1 and a 1, so we get a 1, 0, a 1 and a 1, so we get another 1, 0, and a 1 and a 1, so we get another 1, 0. And then this 1, since we're only looking at a 4-bit number right now, this 1 that we technically have here would just fall off. It wouldn't be counted in the number. So looking at this 0, 0, 0, 1, so this is equal to 1, so we're expecting to get 5, and we didn't. So basically this number, this signed magnitude representation doesn't work for the addition algorithm. As far as the signed magnitude representation, the one positive that people like about this is you can easily look at your number and see if it's positive or negative. So all of the positive numbers have a 0 as the most significant bit, and all of the negative numbers have a 1 as the most significant bit. So that's the one advantage. But this isn't normally used for negative numbers just because of this math limitation, and also because of the wasted bit. So there's another scheme for representing negative numbers, is what's referred to as 1's complement. And you'll also see this called signed 1's complement. And so remember, signed means that we're representing negative numbers as well. And so what all this does is invert the bits. Let's say that we have, well, so 0, 0, 0 is 0. And if we invert all of the bits, so we get 1, 1, 1, that's negative 0. 0, 0, 0, 1 is 1. If we invert the bits, then we get 1, 1, 1, 0, so that's negative 1. So the advantage of this is that it's easy to perform. I mean, it's really easy to just invert the bits. The problem with this is, once again, we end up with this wasted bit because we have two representations for 0. So we're representing 0 and -0 again. And this, we also can't do subtraction with addition alone with this. We end up with the similar problem as before. We don't end up with the right answer.